William Paterson University, who will speak about on a subset of ordered trees enumerated by a subsequence of Fibonacci numbers. We will take Melkamu out for dinner at 6:45 at Indochine on George Street. Everybody is welcome, but please let me know immediately after the talk where they can come at 6:45. Thank you.
All right, thank you again, Dr. Z, and the organizers of this seminar for giving me the opportunity to speak again. Today I'm going to be talking about some subsets of ordered trees. Right now it's some subsets, but later on you will know which subsets I'm talking about. And then some of those subsets that I'm going to be talking about, the subsets of ordered trees, you will see are going to be counted by not the entire Fibonacci numbers, but by some subsequence of the Fibonacci numbers. Okay? And this is just the rough outline of what I'm going to be talking about. In the introduction, I'll just talk about some of the motivations behind looking at subsets of ordered trees. And then the main things that I'm going to be talking about are these two topics, 2 and 3. Contiguous fountain of coins and ordered trees, and then the so-called directed column convex polyominoes and ordered trees. And this is just a byproduct of some of the things that I'm going to talk about here. Okay? And then in the end, I'll give you some references just in case you like some of the topics that I'll be talking about and you want to read for yourself. I'll give you some relevant references on that. All right, so I'm going to start by just saying this. I would like to dedicate today's talk to one of my mathematical heroes, Wilf, who unfortunately passed away last year. I didn't get a chance to go through his services, so at least I felt like I got to do something, so I would like to dedicate today's lecture to unassuming mathematical giant who really treated everyone, big or small, with respect. Rest in peace. So I'm going to start with a definition of fountain of coins that Herb and Andrew Odlyzko gave in one of their papers. And here, by a Kn fountain of coins, we mean an arrangement of K coins. K is the total number of coins in your arrangement, such that there are exactly n coins in the bottom row, and also each coin in the higher row touches exactly 2 coins in the next lower row, and so on. For example, if you take, my drawing here is not the best, but for example, if you take this particular coin here on the top, it's expected to touch exactly 2 coins in the bottom row, and so on. So this is just an example of a fountain of coin in which you have 28 coins altogether and exactly 12 coins in the bottom row. So we got 2 parameters here. You look at the total number of coins as well as the number of coins that you put in the bottom row. So we're going to define 3 things here. First, I'm going to look at the number of Kn fountains of coins. And then if we sum up over all n, then we get f of k, and this counts the fountain of coins by total number of coins. And if we sum up over all k, this one will count the fountains by the number of coins in the bottom row. So I got 3 things here. Okay? So you count either with the 2 parameters or you eliminate 1 in each of these 2. Okay? If you do this, I want to ask you as to which one of these 3 is kind of easy to determine. For some of you probably might say, yeah, all 3 of them are easy for me to count. Okay? But that's why I put the easy thing here in quotes. Okay? So what would you say, Dr. Z? Which one of these 3 you would suspect would be easier structurally to count?
I would say f of k.
F of k? Okay. How about the rest of you?
H of n for variety.
H of n. What would you say that?
I don't know. You can kind of break it up into just how many. I don't know. I have no idea.
So, all right.
There, you wouldn't have put it there if it wasn't important.
Yeah, do that. You can get an almost Catalan-like thing.
Okay. All right, so let's look at it together, and then we'll find out whether or not Dr. Z's or your guess is the correct one, or it's neither of the two.
I hope it's one, then we're all right.
Okay, so here Wilf defines a Kn fountain to be primitive if it's next to bottom row, contains no empty position. That means its next to bottom row will have n-1 coins. By definition, you have n coins in the bottom row. So if the next to bottom row contains n-1 coins, he calls it primitive. Okay? So here, let's introduce a new function, g, which enumerates all primitive Kn fountains. And now if you peel off that bottom row, you immediately get this relationship between f and the new g. That's kind of clear, right? You're removing the bottom row with the n coins, so therefore you get this relationship. For every primitive arrangement of coins, you have, after you remove the bottom row, this is what you're going to end up with. Okay? So that one doesn't have any restriction on it, and therefore you get this nice relationship between the two. Okay? And also, let's define f to be any Kn fountain, and suppose that the first empty position in the next to bottom row is going to occur at R, okay? Where R is any number between 1 and n-1, okay? Now here, I'll show you a picture. Draw a line to the right of the R's coin in the bottom row and split this F, the coin that the arbitrary coin fountain of coin that you picked, into a primitive fountain of this size and not necessarily primitive fountain of this size. So by this I mean taking an example like this. Okay? If you look at the example that I showed you before, the 2812, the first empty position is at R equals 3. So you draw a vertical line there and you split it into two. The one to the left is going to be always primitive, the way you split it. But the one to the right is not necessarily primitive. It's going to be another fountain of coins with a less number of coins and so on. Okay? Now from here, since this kind of factorization is unique, the way we picked here, you can see that f of kn satisfies these summation formula here. Okay? So here, obviously, we take the initial condition for f00 to be 1 and g00 to be 0, so that calculations will be easier later on. Okay? So this is the empty case for the fountain of coins, and this is just for convenience. Okay? So from here, now we're going to define two-parameter ordinary generating functions, one on the fountain of coins, f of xy, the original one, and one for the primitive fountain of coins. And using the equation that I just described before, okay, it's easy to see that this is just a Cauchy product that f will be equal to, if you look at the previous thing that I showed you here, this one, from this relationship, it's quite easy to see that f is going to be equal to 1 plus f times g. It's just a Cauchy product, 1 being the empty case. Okay? Now, the other relationship is going to come from just looking at the generating function for g. This is for the primitive one. We replace g of kn by equation number 1 that I provided to you before, and you go through the routine, and you notice that g satisfies these kind of functional relationship. Okay? So if we put the two together, okay? So the f equals 1 plus df, okay? And the one that we just get here, g of xy, okay, is equal to xy times f of xy. You combine these two together, then it's not difficult to see that you're going to be getting this form of continued fraction representation for f of xy. So this is the two-parameter ordinary generating function for the kn fountain of coins. And then by putting together the two equations, you see that the generating function satisfies this continued fraction form. Okay? So the two of you claimed that the second and the third were easy to get, but my way of looking at it is when you have more variables, you have more structure, and therefore those are easier mathematically, in my opinion, to get. And that's why we are able to get the generating function for the first one very easily like this. And the other two, actually you get them by specializing this particular one.
It depends on what you call easy.
Okay.
Easy to derive.
So that's why I
describe.
Okay. That's why I put the easy thing in quote. Okay. So structurally speaking, the more variables you have, the better it is, I think. Okay. So now we have this generating function. The rest of it, By the way, this problem is a similar problem is mentioned in Stanley's book, problem 6.34. And you will see that the generating function that he's talking about is remarkably similar to this, but he came up to that generating function using the lattice path interpretation, not the coin thing. So if you are interested, you can look at this identity in his book and compare it to this.
It's also similar to the old Ramanujan continuous function.
Yeah, we're getting there. You're right. Okay. So so then if we specialize y equals 1, then we obtain this generating function, which of course is the famous one of the famous Ramanujan's continued fractions, and we can see that this is one of the combinatorial interpretations to Ramanujan's famous continued fraction identity. By the way, speaking of Ramanujan, I brought in this poster celebrating Ramanujan's 125th birthday. This is a poster that's sent to our department from AMS. I'm sure it was sent to Rutgers too. I don't know if they posted it. And one of the identities that's in this poster is the same exact thing that you see there, where x is replaced by q, and the minuses can be adjusted to give you the pluses and so on. Okay? So the point I'm trying to make is we can easily get the so-called deep identities in AMS posters by playing the coin game in combinatorics. So that was the first specialization. That answers the second question. It's going to be the Ramanujan identity there. And then the third one, if you specialize x to be 1, then as you correctly predicted, we get this one, okay? And this is not as difficult as the Ramanujan continued fraction. This one is quite easy, and it can be rewritten into this functional form, and when you solve it, you get the usual Kaplan generating function, and therefore the fountain of coins, if you pay attention only to the bottom row, is simply enumerated by the sequence of Kaplan numbers. Okay? So the third one is actually the easiest of all the three if you look at it, at its face value, because it's just enumerated by the sequence of Kaplan numbers. Okay? How we get to it is a different story. And also this particular simple problem is mentioned as problem 619 in Stanley's book. It's just the point connection and so on. And now to one of the topics that I wanted to get to. What I talked about so far is just a motivation towards what we're going to be talking about today. Okay? So first, the contiguous fountain of coins. This is the same fountain of coins that we looked at before, but in this case, we do not allow gaps. Okay? So every row in here has to be continuous or contiguous. Okay? So it's not difficult to see that CF of n, by CF I mean contiguous fountain of coins, in which there are exactly n coins in the bottom row. That's what I'm denoting by CF of n is. It's not difficult to see that this thing satisfies this kind of recurrence relation. Okay? So the n minus j here means, possibly for j equals 1 to n minus 1, I just included n in there. It's possible for you not to have n minus j, okay? Spaces with coins and so on, you can move them around. It's easy to get this. And from this recurrence relation, you notice that the generating function for enumerating contiguous fountains of coins with exactly n points in the bottom row actually is this rational function, okay? It's easy to get from the previous recurrence relation that I got, the standard snake oil method from which. And also, if you look at the first few entries of this rational function, you look at series expansion, you notice that these terms are every other Fibonacci numbers. By our terms of Fibonacci numbers, I mean every other Fibonacci numbers, where I use the initial condition of f0 equals 0 and f1 equals 1. You will immediately get those things. So that means the contiguous fountain of coins are enumerated by odd terms of Fibonacci numbers or every other Fibonacci numbers. Okay? Now, let me change gear now and talk about a subset of ordered trees, which in this case we refer to as skinny trees. Okay? So let's look at subsets of ordered trees. I assume that you all know ordered trees, so I'm not going to worry about the definition of ordered tree. Where no two vertices at the same level have different patterns. Shapiro and Chen, in a recent paper, referred to these kinds of ordered trees as skinny trees. Okay? Just to see whether or not you're with me, I want to draw two trees with 5 edges here, and ask you guys whether or not you're with me. Okay? Which one of these two trees on 5 edges would you consider a skinny tree?
The second one there.
The one on the?
Yeah. The man.
Yes. The top one is considered to be non-skinny because you have these vertices, at this level, for example, they have different patterns. So this is non-skinny, and we'll consider these kind of things skinny. Just to make sure that, because we're going to be talking about, yes?
I'm sorry, real fast, that unbatted, almost double negatives. Is that saying that a tree is skinny means any two vertices at the same level need to share a parent?
Yes.
Okay,
yeah.
Thank you.
So if you have like more than one vertex, at the same level, and you want those guys to have the same parent.
In other words, in every generation, only one person can procreate.
Yeah, that's what it is. yeah, that's what we're saying. Okay? All right? So if we denote the number of skinny trees now by st of n, just like the contiguous fountain, and we look at the generating function, usually these ordered trees, in recursive form, they satisfy this kind of decomposition rule. This is not very difficult for you guys to see. Okay? The skinny tree is going to end either at level 1, or if it extends beyond level 1, it's going to have this kind of structure. You can only have one of the guys extending and so on. You with me? Okay. So now, every non-empty skinny, blah, blah. I already said that. And now, you can just write down this functional equation for the generating function of skinny trees. What you see here is the one that ends at level 1. I'm considering non-empty ordered trees, and therefore they're going to be a z there. Okay? The ones on the second side, the one that don't end, at the first level, they're going to satisfy this kind of equation, and you add up these things, you solve for st of z, and you get the same rational generating function again. Have we seen these before? This is the same rational generating function that the contiguous fountain of coins satisfy, and therefore we have a small theorem here. The number of contiguous fountain of coins with n coins in the bottom row is equal to the number of the skinny trees with n edges. So we do have the generating function proof here. It's quite simple, undergraduate type thing. But myself and my colleague Dr. Jani, we are kind of obsessed with providing bijective proofs to these kind of things. So we didn't like the generating function thing, so we wanted to provide a bijection between contiguous fountain of coins and skinny trees. And that's why I drew that thing over there for you. Okay? That's the example that I have there. And now here is the description. I'm not going to bother with this thing. Okay? This is the description of the algorithm that we came up with to go from a fountain of coin, a contiguous fountain of coin, to skinny trees. And here is an example. And all you need to do, if you want to draw the corresponding skinny tree to this one, you draw diagonals, and you label your diagonal. This is just for convenience purpose, okay? You label the diagonals 1 through 12 here, because you have 12 coins in the bottom row. And now, the number of coins along each diagonal will determine at what level each of those vertices are going to be, okay? So you have 12, coins in the bottom row. That means the corresponding skinny tree will have 12 non-root vertices. You with me on that? So I'm going to start with the root. And the one that have only one coin, you see, number 1, 11 and 12 are going to be children of the root. You with me? So this is 1, okay? 11 and 12, okay? Now look at the ones with 2 coins on them. Which one are they? 2, 3, 4, 9, and 10, right? The rule here, the connection rule is 2 has to be connected to 1 because they are next to each other, okay? And everything else is going to be at the same level connected to 1, okay? So 2 is going to be connected to this, and the other guys, because of they have to share a parent, right? You have decided that, and therefore 2, 3. What else do I have? 4, right? Then these 2 guys also. I got 9 and 10, right? Okay. 9 and 10. Okay. All of those are going to be at level 2, connected to 1. Do we have a 1 with 3? We got 3 there, 3 coins. Which one is that? 5. And you want that to be connected to the next one, which is 4. Okay, my rules state that. So this is 4, so this is going to be 5. Do we have any other with a 3? That's the only one, right? Okay. So that means the one with 4, 6 will be connected to 5, right? So 7 and 8, they all have the same number. Since they have to share a parent, I cannot have a new parent, so it's going to be 7 and 8 there, right? And that's it. We got everybody in. So now, this contiguous fountain of coins with 12 coins in the bottom row corresponds to a skinny tree with 12 non-root vertices, and this is how it is. And the labels are just for convenience, and you drop them. And going back is also quite simple. The description of going back is here. All you need to do is these guys, the ones at level 1, okay? You got to look at 1, 11, and 12. Those are at level 1, so those are not going to be a problem. What this tells you is you count the number of non-root vertices and you put 12 coins in the bottom row. And then you put the diagonals along them and so on. For the rest of them, you look at vertices at levels 2 and above. 2 and above. What's the lowest level here? The lowest label that we used in here, from 2 to bottom. 2 to bottom here. 2, 3, 4, right? The levels are 2, 3, 4. The lowest level there is 2, right? What's the highest label there? 10, right? So that means on top of these 12 coins, you're going to put the one between 2 and 10. The next one, you're going to look at labels 3 and 4. Okay? What's the lowest one here? 5, right? The highest is 8. So in the next level, you put between 5 and 8 and so on. You got it? And then the last one is 6, 7, 8. You put it between 6 and 8. And that's how going back is going to work. And therefore, this is a bijection between, back and forth, between contiguous fountain of coins and skinny trees. Okay? All right. Now, the bijection that I just introduced here is between contiguous fountains and skinny trees. But actually, it works. You can extend it to not necessarily contiguous fountain of coins. And for example, if you have this, you can map it to this ordered tree and so on. As I said, the problem was stated in Stanley's book, but the suggested bijection there is a 2-3 step connection with other things, and I believe this is a new, straightforward alternative bijection between non-contiguous, not necessarily a contiguous fountain of coins and ordered trees. I described the previous one because that's really what I wanted. Okay? Now, let's also change gear and talk about a third set of combinatorial objects now. We started with fountain of coins, then we went on to skinny trees, or some subsets of ordered trees, and now let's look at a third set of combinatorial objects here. These are called directed column convex polyominoes. These are first introduced by Emeric and Helmut Prodinger in a paper that they wrote back in 2003. The structures have been there, but this particular discussion. All you have to do is you start with a single cell. You are allowed to add cells either on the top or to the right. That's the only thing you are allowed to do to form the so-called the directed column convex polyominoes. You start with a single cell and you add either to the right or to the top. So here the requirement is that every column that you form is going to be by contiguous cells. And this is just an example of a directed column convex polyomino with 25 cells. Okay? So here is the theorem. The number of directed column convex polyominoes of area n, by area I mean number of cells, okay, is equal to the number of ordered trees of height at most 3. Now we are considering a different set of ordered trees. This time around, we are looking at ordered trees that end at height at most 3. I may refer to these as Emeric's trees sometimes. Okay. Here is an outline of one of the two bijective proofs that these guys gave about the proof of this particular theorem. Okay, the fact that these two are the same. Okay, so you define.
Can I ask a question? The trees had n vertices. The trees had n vertices.
N edges. N edges. N edges. Okay, I stay away from number of vertices throughout my talk. N is the number of edges when it comes to the trees. Okay, so you define a bouquet of size k to be an ordered tree whose root has a unique child from which k minus 1 edges are going to be connected. Okay, so here your bouquet is, you start with the root, there's going to be one edge connected to that, and then you have that, and then these guys here are k minus 1 edges. Okay? So this is what we call a bouquet of size k. There are k edges, and it's a tree of height 2, consisting of k edges. You with me on that? Okay. Now, suppose a directed column convex polyomino pi of area n, that means number of cells, has width w. Width is the number of columns. Okay. And assume the i's column extends from level AI to level BI. So I tried to draw the example here for you. This is the example that I showed before. There are 8 columns here, and the level starts at 0 and ends at 7. So we're starting from 0. This one is the bottom one, and this is the top. Okay? You with me on that? AI is the bottom level. BI is the top level for each column. For example, if you take this one, A1, okay, is going to be 0, and then B1 is going to be 2, where it ends. Okay? You with me on that? AI for the bottom level, BI for the top level, where I is the column of your directed column convex polyomino. There are 8 of them in this one. Okay? Now, to the directed column convex polyomino pi, we associate an ordered tree tau defined in the following way. So the root of tau has degree BW. Okay, that is the top of the last column here. So for example here, if we write down these things quickly, if you can help me with this, for example here, for AI, so you're going to be having what? The first one, it starts at 0, ends at 2. The second one starts at 0, ends at 3. Third one starts at 0, ends at 6. Fourth one starts at 1 and ends at 7. Fifth one starts at 3 and ends at 4. Sixth one starts at 3 and ends at 6. The next one, 3 and 6. The last one, 4 and 5. So this is going to determine the number of, the last one is going to determine the number of children of the root in your ordered tree. So for that one, the ordered tree that we're going to draw, is going to have, the root is going to have 5 children in. 3, 4, and then 5. Now the next step asks you to label the children of the